Hi, Mr. Green here, going to take you through the next section of the waves topic for GCSE Physics from the AQA syllabus. This lesson is about uses of waves for exploration, and our learning objective is to know how waves can be used to explore objects that can't be easily seen. You can pause the video and take that down as your lesson objective. Okay, so we have some retrieval practice questions for you to try here. If you could pause the video and restart when you'd like the answers. Okay, so question 1. What's the range of human hearing? That would be from 20 Hz to 20,000 Hz. How do sound waves travel? Vibrations of particles in matter, so the particles pass that vibration on to the next one. Why does sound travel faster through solids than they do in gases? Because the particles in a solid are much closer together, so this passes the vibration on a much higher rate. What's the law of reflection? The angle of incidence is equal to the angle of reflection, so whatever angle the wave hits the boundary at, it bounces back at the same angle. And what three things can happen when a wave encounters a boundary? It can either reflect, transmit, travel through it, or absorb, soak into that object. Okay, our learning outcomes today are to know how ultrasound can be used in different scenarios and to know how seismic waves can give evidence for the structure of the Earth. First up, what is ultrasound? Let's define that. Now, humans have an upper limit of the frequency we can hear. This is around 20,000 Hz. Sounds above this frequency we generally refer to as ultrasound. We need to know three different uses of ultrasound or high frequency sound waves. First up, medical uses. Second up, industrial uses. And finally, echo sounding, which uses high frequency sound, not exactly ultrasound, okay? What are the properties of ultrasound then? Well, ultrasound behaves in a very similar way to normal sound waves. When ultrasound waves encounter a boundary, they're partially reflected, and this is why they're so useful to us. We can use that reflection to work things out. As they've got such a short wavelength and a high frequency, they carry lots and lots of energy. So if ultrasound has a frequency of 30,000 Hz, and a speed of 330 meters in air, what's its wavelength? Use your wave equation to calculate that. Pause the video whilst you do that. Okay, so speed is frequency times wavelength. So we rearrange that. Wavelength is speed divided by frequency. So the wavelength would be 330, which is the speed of sound in air, divided by 30,000, which is the frequency of ultrasound, giving us a wavelength of 0.011 meters. Okay, so medical uses of ultrasound. Our first one is to break up kidney stones. Now, waste products in the blood can occasionally form crystals that collect inside the kidney. Over time, crystals might build up to form a hard stone-like lump, and after a kidney stone's formed, your body will try and pass it out when you wee. Now, sometimes those kidney stones will be really, really large and they'll become too painful to pass out naturally and far too large to come out. Now, what we can use is we can use the ultrasound to shake those kidney stones, to vibrate them so they break apart into a powder, making them much easier to pass. Ultrasound can also be used this way to clean delicate equipment, like really old watches that need a bit of a clean. We can use them to do that. Next one would be prenatal scans. In order to track the progress and health of a growing fetus, it's really beneficial to scan the baby and have a look at it whilst it's in the womb to make sure it's progressing the best way it can. Why don't we use X-rays for this? Pause the video whilst you answer that. We don't use X-rays because they carry too much energy and they are ionizing radiation, and this could harm the still developing fetus. It could cause damage that the baby would then have for the rest of its life. So using ultrasound is a lot safer. The ultrasound partially reflects off each tissue boundary as it passes through the womb. Now, the time taken for each reflection to reach the detector can then be measured, and we can manipulate that data to create an image of the tissues underneath it. This causes no harm at all to the fetus. So we can see there, the ultrasound transmitter sends ultrasound on, and every time it encounters a different type of tissue, it will reflect. If we can see how long it's taken for that to reflect, we can work out the distance away, and we can use our computer technology to build up a picture of that fetus inside the womb. We also have an industrial use of ultrasound. We can use it to detect cracks inside metals. So the ultrasounds pass through the material to be tested, and if it encounters a crack, the ultrasound will reflect back and be detected by the detector. The time taken for that reflection to come back can be used to calculate the location of the crack in the material. So again, it means we won't use materials that are damaged, we won't use metals for pipes which would then be under some stress and maybe break. Finally, our use of high frequency sound is echo sounding. Now, high frequency sound waves can be used to detect objects in deep water and to measure water depth. The time between a pulse of sound being transmitted and detected and the speed of sound in water can be used to calculate the distance of the reflecting surface or the object. The process is really similar to ultrasound imaging, but the sound waves are within normal hearing range, so we can identify objects rather than internal structures. This technique we apply in sonar systems to find shipwrecks, to find submarines, to find shoals of fish, to find the depth of water in many different occasions. It's also used by bats and dolphins, called echolocation. They detect their surroundings and find food using that when there's not much light available. Okay, so speed of sound in water is 1,481 meters per second. Now the sound pulse is emitted from the ship and returns 0.8 seconds later. How deep is that water? Pause the video whilst you attempt that question. Okay, so speed's distance over time. We rearrange that. Distance is speed multiplied by time, so the distance would be 1,481 times 0.8, giving us a distance of 1,184 meters. But this is echo sounding. So the echoes travel down to the surface, down to the bottom of the water and then straight back up again. So it's travelled twice that depth. So the actual depth would be half that distance. So that would be 1,184 divided by 2, giving us a depth of 592 meters. Okay, we've got some questions here for you to do. 4 questions on this slide and some on the next. Please pause the video whilst you attempt these 4 questions. Okay, what frequency does ultrasound start at? That starts at 30,000 Hz. How is ultrasound used to treat kidney stones? The vibrations from the ultrasound cause the stones to vibrate, and these high frequency vibrations cause the kidney stone to break up into smaller pieces, allowing them to be passed more easily. Why can ultrasound be used to provide images of a fetus in the womb? Ultrasound partially reflects when it meets different tissues in the body, and the time taken for the reflection can be used to calculate distance and density, which can then be processed to build up an image of the fetus. Why aren't X-rays used to observe fetuses in the womb? Because they're ionizing radiation, and so they could cause harm to the fetus. Okay, 2 more questions there. Please pause the video and attempt that. Okay, how is ultrasound used to detect faults in metals? An ultrasound pulse is placed through the material, and if there's a flaw in the material, the ultrasound pulse will reflect back to the detector before it should do. The time taken for that reflection to reach the detector can then be used to calculate where the flaw is. Question 6. A high frequency sound wave is emitted from a fishing boat to determine the depth of water. The wave takes 1.2 seconds to return. Sound travels in water at 1,481 meters per second. How deep is the water? So again, we go by that same method. Rearrange the equations of distance, speed times time. 1,481 times 1.2 gives us a distance of 1,777.2 meters. But because it's an echo, it's travelled twice the distance, it's gone there and back again. So we divide that distance by 2 to give us 888.6 meters. Okay, another use of waves, we can use seismic waves. Seismic waves happen when an earthquake happens. When that happens, rocks suddenly move and crack really, really deep in the earth. The place where this happens is referred to as the epicenter. There's the epicenter of one earthquake, where the star is there. The rocks shudder and vibrations spread out from the epicenter, and those vibrations will cause seismic waves. There are 2 types of seismic waves. These are P waves and S waves. How do we measure them? We use something called a seismometer. A heavy inert mass with a certain resistance to movement, which is inertia, so it's not going to move easily due to its weight, is suspended from a frame by a spring that allows movement. The energy from any seismic activity excites this mass, causing it to vibrate. So it looks like this. So if the earth vibrates, that mass will move up and down, and we can take that scale on the graph next to it. Scientists can work out the location of an earthquake by calculating the time difference between the arrival of the P waves and the S waves. Information from 3 different seismometers is used to work out the exact location of the epicenter, such as that. So there's the difference between S waves. S waves are longitudinal, travel really fast, and they can travel through solids and liquids. P waves are transverse. They travel a lot slower than S waves, and they can travel through solids only. Now this is really important when it comes to using them to tell us about the structure of the Earth. We can't directly observe the internal structure of the Earth, so seismic waves give us evidence for it. Seismic waves from large earthquakes are detected around the world, and their paths are curved because the waves refract due to the gradually changing density of the layers. S waves are not detected on the opposite side of the Earth. Now we know S waves can't travel through liquid, so this suggests the mantle's got solid properties, but the outer core must be a liquid because S waves can't travel through them. You can see there from the S wave patterns, anywhere where there's solid it will travel through. As soon as it gets to that liquid core, it stops. So we can see on the other side of the Earth we don't encounter, we can't take those S waves, we don't detect them, meaning it's not travelled. So this gives us strong evidence that the outer core is made from liquid. P waves are slightly different. P waves are detected on the opposite side of the Earth, but refractions between the layers cause 2 shadow zones. They cause the waves to interfere with each other, and there's no P waves detected there. The size and position of those shadow zones indicate to us that there is a solid inner core. We can see the path that it should take, we can see the path that it is taking, and because of the path it is taking, because it's bent so much, we can tell from that there is a solid inner core. Okay, so a few questions for you to answer on this one. Pause the video whilst you attempt those. Okay, question 1. How are seismic waves generated? Generated when earthquakes happen and they cause the rocks to shake and vibrate, which causes the seismic waves. What device do we use to measure the seismic waves? We use a seismometer. 2 differences between P waves and S waves. P waves are transverse, they're relatively slow, and they can travel through solids only. S waves are longitudinal. They travel relatively quickly and can travel through solids and liquids. Question 4. How do P waves and S waves provide evidence for the internal structure of the Earth? S waves aren't detected on the opposite side of the Earth. Now because they cannot travel through liquid, this tells us that part of the core of the Earth must be made of a liquid. P waves refract between layers, causing shadow zones on the opposite side of the Earth, so where they should go through, they don't, and they bend. The size and position of these zones show us there is a solid inner core. Okay, hope that was useful for us. Please review any more of the videos on our YouTube site. Thanks very much for your attention. See you soon. Goodbye.